All right, let's jump right in. Today we're talking about a field that completely changes the game for public health, and it does it by asking one simple but incredibly powerful question: where? This is spatial epidemiology, and it's all about the idea that where you live is deeply, fundamentally connected to how you live and how healthy you are. And just so you know where all this great info is coming from, this whole explainer is based on the first part of an amazing lecture series called Basics of Spatial Epidemiology by Professor Olin Raju Lawal. So we're basically getting the highlights from a masterclass on how our maps shape our health. I mean, think about it. You've probably seen this in your own life, right? Why can one town feel perfectly healthy, while the one just a few miles down the road seems to struggle? Well, it's not just random chance, and spatial epidemiology is the science that digs in to find out why. Okay, so let's get right to it. Before we can get into the why behind those differences, we have to nail down the what. What exactly are we talking about when we say spatial epidemiology? So at its heart, it's the study of how diseases and health are spread out across a map. Professor Lawal's lecture explains it as a mashup of three different fields: epidemiology, geography, and statistics. You know, a traditional epidemiologist asks who gets sick, with what, and when. The spatial epidemiologist comes in and adds that crucial fourth piece of the puzzle: where are they getting sick? Now, before we can start drawing our own maps and spotting patterns, we've got to learn the fundamental rules of the game. These are the core ideas that every single spatial epidemiologist has to live and breathe by. And this right here, this is rule number one. It's Tobler's first law of geography, and it's pretty much the bedrock of this entire field. It sounds kind of simple, but it's profound. It just means that the things right around you, your local park, the corner store, your neighbors, have a way bigger influence on you than things happening across the country. To put that another way, and this is a really powerful way to think about it, your zip code can sometimes be more important than your genetic code. Now, that's not to say genetics are irrelevant, of course not, but it hammers home just how much things like local air pollution or whether you have access to fresh food, all things tied to where you are, can dramatically shape your health. But this brings us to a huge, huge trap you can fall into called the ecological fallacy. So let's say you find that a city with a lot of green space has, on average, a really high life expectancy. The fallacy is jumping to the conclusion that every single person who lives there is healthy because of the parks. You're taking a broad, group-level fact and just assuming it applies to every individual, and that's a big mistake. And here's another big gotcha you have to watch out for. It's called the Modifiable Areal Unit Problem, or MAUP for short. The first part of it is the scale effect. Think of it like this. If you analyze health data for an entire city, you might see one pattern. But if you zoom in and look at it neighborhood by neighborhood, a totally different story could pop out. The answer you get literally changes depending on your zoom level. And the problem gets even trickier with the second part of MAUP, the zoning effect. So even if you stick to the same scale, say you decide to look at neighborhoods, how do you draw the lines for those neighborhoods? Seriously, if you draw the boundaries one way, you might find a big disease cluster. But if you just shift those lines a little bit, that same cluster could completely vanish. The way you slice up the map can totally change your results. Okay, so knowing the rules and the major pitfalls, what tools do epidemiologists actually use to get the job done? Let's go ahead and open up the toolkit. The first and maybe the most foundational tool is disease mapping. And this is way more than just coloring in a map. It's a really careful process to show where disease risk is truly high or low. To do that, analysts will often compare the number of cases they actually see in an area to the number they'd expect to see, which helps them find the real problem spots. So once you've got your map, you want to find clusters, and there are basically two ways to go about it. Global methods give you a single verdict for the whole map. They answer the big question, overall, is there any pattern here, or is it all just random? But honestly, the local methods are often where the real magic happens. They go in with a magnifying glass and pinpoint exactly where the hotspots of high disease rates are and even where the cold spots of unusually low rates are. Now, this is where things get really clever. What do you do if you're looking at a super rare disease or maybe a tiny neighborhood with only a few people? The data's going to be really unstable. Well, Bayesian models solve this by borrowing strength from nearby areas to make a more stable, more reliable guess. It's a statistical way of smoothing out the noise when you don't have a lot of data to work with. And finally, what if you only have data points from specific spots, like, say, a handful of air quality monitors spread across a city, but you want to know the pollution level everywhere? That's where geostatistical methods come in. They use the points you do have to make intelligent predictions about the values in all the empty spaces, creating this amazing continuous map of risk. Okay, so we have concepts, we have tools, but what's the so what? Why does any of this matter? This is where we go from theory to real-world life-saving action. And as Professor Lawal's lecture series makes crystal clear, the applications are massive. This is all about turning data into action. It guides public health planning, powers real-time disease surveillance, helps us track down environmental risks, and is a vital tool in the fight for health equity. Let's make that super concrete. By mapping out where sick people live and where the clinics are, officials can see with pinpoint accuracy the exact neighborhood that needs a new clinic most. Or they can figure out which communities to hit first with a mobile vaccination van. It's about putting resources where they'll do the most good. I mean, we all just lived through the biggest example of this in our lifetimes. Remember those real-time COVID-19 hotspot maps? That was spatial epidemiology live and in action, helping officials see where the virus was flaring up so they could rush in with testing and resources to get it under control. And this is a powerful tool for justice. By layering a map of, say, childhood asthma cases on top of a map of industrial polluters or major highways, you can draw a direct visual line between where people live and the environmental dangers they face. That's the kind of hard evidence that drives real policy change. So if you take one thing away from this, let it be this. Our health stories are written all over the landscape around us. Spatial epidemiology gives us the language to read that map, to understand the story it's telling, and, most importantly, to start rewriting that story for a healthier future for everyone. So that leaves just one question. What health stories are hiding in plain sight right outside your front door?